eso?
¿Qué tal? Muy buen día a todos. Muchísimas gracias por asistir a este seminario. Tenemos la visita de un profesor muy destacado de la Universidad de Torino, de la Politécnica de Torino, el doctor Marco Barla, que nos dará una plática titulada El rol de los sistemas de monitoreo y alerta temprana en la gestión de problemas geotécnicos y amenazas climáticas. Entonces, antes de darle la palabra, voy a leer una pequeña semblanza al doctor Barla. Él es profesor asociado de Ingeniería Geotécnica en el Politécnico de Turín y es consultor experto en problemas de túneles y estabilidad de taludes. Él dirige un grupo de investigación en el campo de pruebas de laboratorio en suelos y rocas, modelado numérico, excavación de túneles, estabilidad de taludes, monitoreo geotécnico y geoestructuras de energía. Es editor en jefe del ASCE, International Journal of Geomechanics, presidente de la plataforma de grandes instituciones geotécnicas europeas y desempeña funciones académicas como asesor del rector para actividades deportivas, miembro del sistema de control de calidad de la universidad y miembro del consejo de departamento. Marco Barla es autor de un libro de texto, es titular de 2 patentes y ha publicado alrededor de 200 artículos científicos en revistas arbitradas y memorias de congresos nacionales e internacionales. Tiene más de 20 años de experiencia como consultor y fundador de GeoSolving SRL, una empresa de ingeniería incubada en el Politécnico de Turín. Pues, Dr. Barla, thank you very much for accepting the invitation, and go ahead, the floor is yours.
Thank you. Muchas gracias. Thank you, Miguel. Together with the John Duyotto, I forgot to give you, because there is also it's an invitation to publish on the International Journal of Geomechanics. You do super research. I had a nice visit to your lab, and I appreciated that very much. And so if you have papers on constitutive modeling, of numerical modeling, on geotechnical engineering, and geomechanics, please send it through. The impact factor is quite high, and the review process is not that quick, but let's say we try to do the best. It's in line with all major international journals. So later I'll give you the hint. Then I'm very happy to be here, and thank you for attending. When we spoke with Miguel, we said let's have as a topic of the presentation early warning systems, because we've been working a lot on this, both on an academic side and on the practical side. So I will maybe go through some ideas here, and just look at the time, and then Miguel, when I need to stop you, you make like this, okay? So I don't get lost. So what we will refer to today are these kind of phenomena. Here you see a motorway in Italy, close to where I come from, which is the city of Torino, and a debris flow landslide that caused the collapse, and we want to avoid that, or at least detect it in advance. Now, why do we deal with these issues in Italy? Because look, Italy is a country in Europe, you know that, and Torino is somewhere up there, very close to the mountain. This region is called Piemonte, which I think in Mexican you say al pie de la montaña, Piemonte. So you know what that means. We are at the foot of the mountains. These figures here are for Italy, but they will be similar. Well, the photos are from Piedmont. This is a mountain called Monviso, where the river Po starts, is somewhere there. These are the vineyards, where the Barolo wine and Barbaresco and so on. And these are the rice. Where we have plains, we grow rice. So if you look at these figures, you see that we have a lot of, it's more than 70% of the land is hill and mountains, so that means we have a lot of landslides. And that's the reason why we are interested in these topics. These are pictures from where I come from. It's this is the city, that's the symbol of the city, it's a tower, and it was the capital of Italy in 1800, so that's why we have many royal palaces, and this is the headquarters of the Politecnico, of my institute. Well, I don't have the office here. We are in a new building, which is much less nicer than this one, but at least we can say we have a nice headquarters. Okay, so I will go through, by the way, please interrupt me at any time if you think something is not clear or you prefer to go into more details. I will just go through briefly what is an early warning system and what I think are the key aspects to build an early warning system. And so we will look about monitoring tools, modeling, thresholds, and if we have time, we can see a short example of it. Now, why are we interested in this? Yes, because we have a lot of mountains and hills, as I said, but also because we have climate trends all around the world, as we know, and this, of course, is a picture of Europe. And in this area of Europe, particularly in the mountain area and so on, we have these facts here, so that we have less precipitations, but they are more intense. I don't know the figures in Mexico, but it's what's happening in my area of the world. So less precipitation over the year. For example, we have less snow to go skiing, but when it snows all the same day, a lot of it, and this causes an increased frequency for phenomena like these ones, which is a debris flow. This is a channel in the mountains, say 1.5 hours from my house, and it's very localized. You see that along this gully, along this channel, during the winter we can have a snow avalanche. During the summer we may have a debris flow. So the occurrence of these phenomena are changing. We have more occurrence of these kind of phenomena. That's the observation. This is the same gully, the same channel, the same one, but in winter after a snow avalanche. You can see it there. And clearly, if this is a road, we want to know when this occurs, and we want to be sure that the car, which is traveling on the road, is not going to go below the snow avalanche. So that's the issue. Okay, we want to build an early warning system to try to save the lives of people driving, advise them soon enough for that. So it stands into, you're familiar with mitigation and adaptation strategies. This stands into the adaptation strategy, if you want. Okay, so what are the key aspects to do that? Well, this is my, let's say, my personal opinions. Well, not personal, there are a lot of people working on these topics and published papers, so I put things together, we can discuss it about it. So what is an early warning system? This is a nice, I think it's nice because it has everything into it. I don't know if you look at that picture, that's a glass, like that one. If a dinosaur was running behind, outside the door, we would see this shaking, and it's an early warning system because it gives us a warning early before the dinosaur come in. So that's the meaning. This is what we want to do. We want to reduce and mitigate the residual risks, because we as engineers or geologists, we cannot take the risk to zero. We have to accept that we have some risk. So this kind of systems are there to mitigate and reduce the residual risk, the risk we are not able to avoid. That's it, basically. So we have a warning system, which is the glass with the water, which includes sensors. The sensor is the glass and the water for detecting the event. The event is the dinosaur running outside the doors, and the decision subsystem. So what will be that? Well, if we see the glass shaking, we run away the other way. Okay, that's the decision subsystem. Of course, these systems are nice if they are able to detect all the events without any false alarm. So if that is shaking, it should be a dinosaur out there, not just a truck driving or collecting garbage or I don't know. Okay, so we need to minimize false alarm. And this is easy to say, but it's very difficult to do in practice. So in order to have those characteristics, what we think is important is that the measurements we take are of high quality. That sounds rather obvious, but we were looking at pressure transducers earlier in the laboratory, and you have many types of pressure transducers. Some are very precise, others are not. So the quality of measurement is something which is important and usually goes proportional with cost. Redundancy in such systems is also very important. So not just to have one sensor, one glass is not enough. We have 3 here, that's redundancy, that's good. And then we need to, this is for geotechnical engineers, I mean, we need to somehow start to make some prediction so that we know what we would expect if the dinosaurs come in, and then we know, for example, what are what we will do in terms of actions. So we have to have a prediction of what we expect, and based on that, maybe we will need to define thresholds. We will speak about thresholds in a few minutes. So 1, 2, and 3 are, in my opinion, one of the most important aspects. We will speak a little bit about the quality of measurements shortly. About redundancy, redundancy applies to all the components of an early warning system. So I said not 1 sensor, but 3 sensors. Maybe not all localized here. Maybe we should put a glass over there. So also spatially. In the case of a really real, not this one, but a real early warning system, for example, also power supply. If we are using solar panels, we need to have a battery. Otherwise, if you only have a battery, it's not enough, and so on. Okay, so everything should be redundant. Of course, this goes together with cost. Look, this is an example. There is a landslide. This is a lake. It's in Italy, and there are many. Each point is a position of a sensor, and you see that. Well, it's in Italian, but I'm sure you can mainly understand that you have different types of sensors. So different positions and different types of sensor and different quantities. So redundancy in more or less everything. And what I would say, prediction and performance, that means that we need to find some way to define thresholds. So when should we start running away? What is the shaking that we want to look at? For example, that glass is almost filled with water. Shall we start running when the water comes out of the glass, or just if we see it slightly? So that's a threshold. We have to define it. It's very difficult to define appropriate thresholds, but that's something we can do by doing geological and geotechnical modeling studies, and I guess you are also expert in these aspects. I'll show some examples shortly. And another key aspect of early warning system is that, at least I think, they are not fixed in space and time. We design them, and then we adapt them. They evolve with time. So at first, maybe we should be more conservative. Once we start to learn things, we can be less conservative, and so on. Here you have many other aspects that you can consider, but you can group all of them, saying that the early warning system evolves with time. It's not fixed in space. Now, so we said quality of measurements. Now, what kind of measurements do we take? Well, we have a lot of sensors out there in the market. You are probably familiar with many of these. Inclinometers, crack meters, topographics, meteor stations, and so on, many others. I just put some photos here. Maybe I'd like to stress a few minutes on 2 specific sensors that we can use, and that I put the word innovative. They are not really, I mean, it's already many years that we have been using this, so it's not something really new. But I think that these particular systems, for example, are very interesting for early warning systems. This is what we call radar interferometry. It can be from the satellite. I'm sure you use it a lot for subsidence here in Mexico, based on what you have described. But now we also have it, what we call ground-based interferometric radar, that we use mainly for landslides monitoring. And it's a radar, so the principle of operation is this, that we send a wave, so it's here, hits a target and comes back, it's reflected by the target. If the targets move, what we see here is a change in the how do you call it, in the phase. There's a phase change. So based on the phase change, using this equation, you compute the displacement. So that's the principle of these techniques. And they're very precise, because we can get, in the case of ground-based radar, we go down to 1/10 of a millimeter of displacement. So it's quite good if we monitor a landslide. So this, for example, this is an example of the ground-based equipment which moves on this track to monitor a landslide. We place it here, and we were monitoring this area on the other side of the valley. This is another example of some results we published some years ago, monitoring this area. It's up in the mountains, and you see here many green points. What are these green points? Well, each green point is a measuring point. So basically here we would probably have 2,000 or even more measuring points. If you just compare this with a total station can have, I don't know, 20, 40, 100 measuring points. Here you have 2,000, and you don't even need to go there and put the target, because it is the rock that is reflecting. The target is the rock itself. So that's very exciting and gives a lot of power for us as geotechnical engineers. Look, in this particular case, here you have a closed view. The added on that we get from this kind of monitoring is really a spatial understanding of the evolution of this particular landslide. You can distinguish these area here, the gullies, from the main landslide body, which is up there, and so on. Okay, we're not going into details, but just to see that we have really spatial understanding of the phenomena. Recently, we used this system also indoors in a tunnel. So it's the same kind of technology to monitor the crown. And consider that it takes a measurement, this one every 20 seconds. So you have a detection every 20 seconds. And the idea here was, why don't we use this for early warning systems in case you have to do maintenance of the tunnel and you have to work there. And when we do maintenance, sometimes in Italy we demolish the crown and we reconstruct the crown later. So when you demolish, you want to be sure that something is not going to go on top on the head of the workers. So this kind of technology, well, I mean, we try to stress it further to be used in this kind of early warning applications. Another type of application is monitoring of buildings. The same instrument, which is this one, was placed here. This is an area in the south of the city of Torino. Along this road comes a tunnel of a metro line. So they started the excavation from here, coming this direction like this, and we wanted to monitor the performance of the buildings during excavation. So you see here the buildings taken from the scenario of the instrument, and this is the monitoring. So the tunnel was coming from down there, coming towards here, and here you see the typical chart where we have displacements versus time, and you can recognize this is the typical chart we expect to have when we have the excavation close to the face. This is probably the position of the face of the excavation, and basically showing the buildings, they were simply following the excavation advancement, the phase advancement. So we could follow it quite closely. And again, this could become an early warning system because we can have a lot of measuring points on the building. It's probably, I don't know, 300 measuring points against the total station that would have maybe 20. And you can use each of these measuring points to get curves like this. And I don't know, if you look at this, what's the color? The green one. If you look at this green one, if you don't see any, if you don't look at all these ones here, there is a sudden increase in the displacement. So if you are there and you see that, you might say, oh, there's something going wrong. You can take an action and so on. But of course, you will never look at only one single point. You can look at many others, and so take actions in a wise manner. Okay, so ground-based radar, I think, is something interesting. It's a relatively new tool there for us to do early warning. Another new tool are fiber optics. We are using them in monitoring structures. And well, I'm not going to go into the details, but we know that the light goes through the fiber, and there are different types of fiber optic. The interesting ones are these ones, what we call distributed, well, in my opinion, because they give an addition to traditional sensors, because it is the entire fiber which is the sensor. So we will get a detection everywhere along the fiber, not at single localized positions. And they look like this. They are just a fiber. I don't know if you can see this orange cable there. That's a fiber optic that we put in a concrete element segment in a tunnel. So it's just a cable that you need to put there. Of course, you will need to connect this cable to a system that we call interrogator, which is a system that sends the light into the fiber and receive it back. It's a loop like that. So these are interesting, and we are trying to apply them to monitor debris flow and snow avalanche along gullies like this, just burying the fiber optics along the gully or placing them on fences for rockfall. This is a rockfall barrier. So that's a project we did at Polito, and we call it like this. It's a patent, and I think that's also interesting. I can show you a few pictures from our lab. This is it's around 3 meters length. It's a very simple slope, a wooden slope. We put some soil on it. We place the fiber on, then we cover it just to be sure that we didn't lose the soil, and then we made blocks rolling down like this to see if we were able to detect something with the fibers. And this is what we did. Look, this is an example where we will soon see something rolling down, and what we see here is what we are reading with the fibers, and this is noise. This is the noise. When a block is coming down, you see that the detection that we get from the fibers is rising up a lot. You will see it colored by red because we have defined a threshold. When it goes beyond that specific threshold, then it activates, for example, a traffic light, turns on red on the traffic light. So that we did a lot of, something like 2,000 tests, rolling down blocks there to try to understand if we could repeat information. Look, if I go back one slide here, the idea is to turn on traffic lights along the road so that a car that travels here will stop before the debris flow comes down. Okay, that's the idea. Good. So that was on monitoring tools. Then the last step is defining the thresholds. So how do we define these thresholds? How can we do that? As I anticipated before, here we need geological and geotechnical modeling. And I know you are expert also in numerical modeling. Now here, maybe we have two ways forward. If we look at the literature and so on, we know a lot of people like to apply what they call phenomenological methods, which basically, I say it in simple words, is looking at observation and deciding thresholds based on observation. So I've never seen that, I don't know, that the velocity in that particular area was higher than 3 millimeters per year, so that is probably a threshold. If I go beyond that, it's something unusual. That's the idea, okay, said in very simple words. A step forward, I believe, is what I called here quantitative analysis, which is what we can do by doing what we're good in doing it. Geotechnical characterization, modeling, validation, and trying to build scenarios and things like that. In order to define thresholds, to build scenarios, long-term prediction, and things like that. Look, I show you an example of a phenomenological approach on a landslide. It's the same photo we saw before. In this particular example, which is in the north of Italy, we had a small landslide in this area here. You see this white area, it's this one here. It fell in 2005, I think. But the concern is on the big one with the contour over there. Look, these data here show the velocity versus time. Well, sorry, this is not the velocity. This is the inverse of the velocity. So it's 1 over the velocity versus time of this collapse. And this is a phenomenological approach that is quite used in practice. If you plot these data inverse of velocity, when you are close to collapse, you can see they are aligned more or less on a line, and you can almost predict the collapse time. Okay, this is what they say. Now, this worked well because it collapsed, so of course they are going exactly on the same date. But we want to do this in advance, clearly. So when we are here, we want to say, okay, I put a line, and I don't have these data points yet, and I want to say that's where I want to go. So let's move on this side, and let's look at data from the whole landslide. And if you look up here, they are quite dispersed. But if you go back some days, also up here, they were quite dispersed. They tend to get closer when we are closer to collapse. And if you look at these data, they come closer, they come closer, they come closer. If you draw a line like this, you can make a prediction and say, I will have a collapse there. But then the data turned. And if you look at this, you can say, oh, okay, it was a wrong prediction. Look, I put a new line now, I have another collapse. And they turn it again. So there's something we're missing there. So phenomenological approach are nice, they might be conservative, but this is how the data I'm plotting here look like, velocity versus time. So it's almost zero somewhere. At a certain point we saw an increase, and then it went back. That's why we saw this. And then it went back. That's it. Well, it's not really surprising. If we look at big phenomena like this that we call deep-seated or large landslide, deep-seated gravitational movements, often they behave, well, this is the creep curve. Often they behave like this. We sometimes see a sort of tertiary creep, but then we get stability again. Then we see like that again. We see acceleration and deceleration. It's something we observe in nature. And of course, the inverse of velocity will fail in all of these until we get really the collapse. So that means we will have false alarm. Remember we said at the beginning we want to minimize false alarm. Otherwise we don't trust it anymore. You know, in Italy we use a joke, we say al lupo al lupo. Do you know what al lupo means? Lupo is the wolf. And you say, oh, the wolf is coming, the wolf, and then the wolf never comes. And so when the wolves come, you're not prepared, okay? That's the thing. So you want to minimize false alarm, otherwise no one will stop at the red traffic light. If they know in the mountain area, there will not be a lot of people living there, but they know the mountain very well, much better than us, and they see the traffic light red when nothing occurs, and say, wow, this is not working. They will never stop anymore. So they have to be confident on the system, and we have to minimize false alarm from that. So I think that numerical modeling is of good help in that. Quantitative analysis, so I think it's clear that I prefer quantitative analysis than a phenomenological approach, even though I do admit that they can be of very help, particularly at the beginning of the studies. And with numerical modeling, we have a lot of options out there. I know you are also, many of you are working with these, finite elements, finite difference, and so on. We're not going into the details. These are examples of, this is the landslide we saw the photo before, and modeling, 3D modeling to try to determine thresholds and long-term behavior. If we are able to build the scenarios, predictive scenarios, then we can try to set thresholds. Look, how do we go for that? You build numerical models. And what we do is look at this plot. This is a chart that we published recently, but for us, the only interesting part is this. we build a numerical model by knowing a lot of things of the geotechnical characterization. So we know that this is time consuming. It's not something that we know in 1 week. But what we do is, if we are able to build something that resembles reality, we can try to apply some actions. The increase of the water table, a seismic action, a reduction of the friction angle, or other kind of actions that you think are most appropriate for your site, and you build a number of scenarios analysis. If you are lucky that you have monitoring data or previous instability, you can also use back analysis to validate what you're doing. But not always we are that lucky to be able to do that. And based on this, we define thresholds. Because with these scenarios, we will have some situations. Look at this chart here. Imagine that this is the displacement and this is time. And that with the green line, this is a situation like the one we monitored. So we apply an action, we see some acceleration, but then we go to equilibrium. We don't want a warning there. We don't want a warning because we're not going towards collapse. But in another situation, so maybe a higher water table, for example, just to make it simple, you go to collapse. So you can distinguish between the scenarios that brings you to collapse from the scenarios that will not bring you to the collapse. And by that distinction, which is not that straightforward as I'm saying now, you can use that information to set thresholds. We will then, if we want to be conservative, we'll put some factor of safety on these numbers and so on, but that's the principle. That's the principle. And in this particular example here, for example, we put 4 different levels. You see here, attention, warning, pre-alarm, and alarm. So maybe this is, you see this are earlier than the green coming down. So these one would be probably false alarm if we were following the green line. But in the case of this example, these two will not cause any, let's say, action to the population or to the people living on the lake or in the industrial estate, which is below the landslide. But it's just something like, if you increase the attention threshold, then increase the number of monitoring. So if you're monitoring every hour, take monitoring every 10 minutes, for example. So that's something that who is managing the monitoring it can do. It's a first stage of warning. And when you go here, then you do actions. Go away, close the industrial estate, and things like that. Typically, we have flow charts like this. This is very small. I don't think you can read it, and then it is in Italian. But look at the green, yellow, orange, and so on. This is clearly nothing is happening. If you exceed the threshold, you enter this, and you will do something. If you go even farther, you enter this one, you will do something else, and so on until everybody has to escape. You also need information to go back to the previous situation. You also need that. Because, for example, in that example I showed you before where the velocity was more or less 0, then it increased and then it came back. It's the same data we saw before. Well, we exceeded the attention level here, the warning level, we never reached the pre-alarm. But then we had a rule to go back to the previous alarm areas. And basically what we do is we say, in this particular case, if we have 5 continuous days below the threshold, then you go back to the previous setting. So that's just an example of how we can build actions out of our result of the modeling. And of course, we can do predictions also for debris flow. So what the example I show here is for a big landslide, but I started saying that early warning systems are important also for debris flows, and with lumped mass methods and other the distinct element methods and other methods, we can, for example, identify. These are clearly gullies in a mountain area. We can identify where we would expect the debris flow to occur. And this is also important, for example, to build early warning system, because we're going to build an early warning system along this galley here, which is probably the one which is more affected, and we're not going to put anything in this area because we're not going to have any effect there. Now look, if I have another 5 to 10 minutes, I will show you a short example of an early warning system for debris flow and snow avalanche. So basically we want to tackle these kind of phenomena, and it's in a similar situation. I think I have a photo here. Yeah, it's a little bit dark, but you see the road there. There is a gully coming like this, another one in this area. And this road is linking a small town on this side to a small town on the other side, a national park here. And it is around a little bit less than 2,000 meters below the sea level. So it's lower than we are than here. But for us, it's high in the mountain, okay? Because we don't live in Mexico. So for us, that's very high in the mountain. It's also very cold. If we connect to the monitoring system now, it's going to be minus something, the temperature up there, and there's already some snow. Anyhow, look, the idea is then you clearly see also from the topography that these gullies are really localized. Well, we will have debris flow going down these gullies regularly. Now, when I say regularly, it's not that regular. You don't know exactly when they will occur. We are monitoring these two since 2017, and we had one debris flow and 2 snow avalanches. Okay, so 2017, we are 2023. It's almost 6 years. Well, the winter is to come, so 5 years, and we had 3 events. So that's more or less the range in this particular situation. There are other areas, for example, in Eastern Italy that are more regular. Every year they have a phenomena there. So you know that sooner or later it will occur. And the idea is to have some detection along the galley and activate some alarm system on the road. Basically turn on a traffic light, for example. This is not, it's not a highway. You will have a car every half an hour going there, or a little more than that, okay? So it is not the intense traffic as you would have outside here, but so for that, a traffic light is enough, okay? That's why you might say maybe a traffic light is not enough. Look, the system will work more or less in this way. You have some detection systems. You have something, let's say, intelligent, managing everything, receiving data, taking some decisions, some algorithms, applying the thresholds that we have identified, and turning on traffic lights or other alarm signals, sending the data to a website where we can read it and see how things are going. Maybe we can operate. We can decide, let's turn on the traffic light, for example, or let's turn it off because it was a false alarm, things like that. These are the kind of sensors that were installed there. These are called pendulums. So you have a cable hanging over the small galley, and the pendulum are hanging like this. There's a clinometer there. You can see it here, and there is just a weight over there hanging. And these yellow and red plastic things are just for visibility, because there are animals. And this is a natural park. They don't want an animal to get the weight in front. And also sometimes you have skiers coming down there. So again, you don't want a skier to find the weight because it's that big and it's not going to be nice. So for visibility, basically. Okay, so it's like that. When the debris flow comes down, it's quite clear. The pendulum is there. The debris flow is coming. Boom. The clinometer will measure an angle. You set a threshold. In this case, it's at 8 degrees. I guess if you have a rotation of 8 degrees, it triggers the alarm. Very simple. Very, very simple system. This is another one. It's just a tape. It's like this along the galley. We have 2 of them, and there is also some connection to the bottom. And you have a box there. I think I have a photo. There it is. When you pull the cable, because the debris flow is coming and is breaking the cable, then this is pull it out, and 1 and 2 are the sensors that will activate the alarm. We'll give the alarm. that you are pulling the cable. Of course, you may have false alarm here if an animal is walking here, is pushing the cable, that will cause a false alarm. So in addition to this, we always have webcams, so that if you get a false alarm, I receive it on the cell phone, and I can go there and look with the webcam. Oh, there is a mountain animal there doing something, and so you turn off the traffic light immediately. It's always useful to have meteo station, because these phenomena are triggered by, we said before, intense precipitations. So this is an information that we can use to tune our thresholds. If it's raining a lot, well, let's be careful. Let's keep the cell phone in our hands, because we will sooner or later receive a message. So this is always very important in an early warning system. And then we have traffic lights. Here you see a photo, a winter photo. This is a path where you go to do cross-country skiing. It's a nice area for cross-country skiing, this area there. And this is let's say, the concept of how it works. In an ordinary condition, the pendulums are there, cars are traveling on the road, information is passed by the system. This is what the webcams will see. There is a webcam on the road, another one up there. If the meteo station tells you, oh, it's raining a lot, it's snowing a lot, then you can say some warning. For example, you can turn the traffic light to yellow, flashing yellow, so people can drive. But you say, well, be careful, because it's raining a lot. Nothing is happening now, but it's raining a lot. So that's why you need a remote control, because you will turn on the traffic light from the Torino office, not you don't go up there to turn it on, of course. And when you have a debris flow or a snow avalanche, the pendulum will be tilted, and this will automatically turn on the traffic light. And you will look at the photos to understand what happened. I think I have a photo of snow avalanche shortly. This is how you look. It's a web platform. There are many types of it. This is the one we use. You see the photos there. You see the data. For example, the battery life, the inclination of the pendulum, meteo data, a lot of data that you can look at, value, and decide what to do. And yeah, this is a photo showing the detection of an event. So here you have, during operation, ordinary conditions, you see that you have a lot of snow along the gully is like this. So we are looking at the cable, and we are looking at it like this from the top. And some days after, so this is 7 January 2018, and then this is the day after, 8 January 2018. And you can, of course, it's not very clear because there is snow and everything, but you can see the snow avalanche went down. This is a pendulum. Here you see another pendulum. So it's not vertical anymore. Now they are rotated. You see the snow avalanche made by many snowballs. It's like a mass of snowballs. And you can check by looking at the webcam on the road, what's the situation in the road, and of course, the second point is then you advise, you phone to the officials, and everything starts to take place. That's it. This is another event we had. That's 2022. It's a debris flow. Again, the gully. The road is down there. You don't see it now. I think you see it better now. This is the road after the debris flow, and a lot of material there. Maybe it's written there, something like 2,000 cubic meters. They just come down almost at once, so you really don't want to be there when this occurs. And once it's there, then it takes a few days to clean the road again, and life starts again. But it's a phenomena that you need to adapt. Okay, it's in the adaptation kind of framework, as we said before. So that's it. Look, just as a final remark. So we said, did I do something? No. I stressed about the quality of measurements. So that's really, if you are responsible for an early warning system, The quality of measurement is really a key aspect. We need to have a look to that and choose the sensors that are appropriate. Redundancy applied in many aspects. And then quantitative analysis to support it, to find threshold, and to try to identify that. That's it. I put this photo because I like when I speak to at least to colleagues and students to put forward this book, because I liked it very much when I was younger. This is it's an Italian author, Primo Levi. You're probably not aware of him. He was he was a Jewish and was in a concentration camp during the war. Second World War, and then was released, and he wrote a book which maybe is the most famous book, which is This a Man? Maybe if you've seen the movies also, it's the famous book, but I like another one, which is this one, which is called, I found the Spanish-Mexican translation, La Llave Estrella, La Chiave a Stella in Italian, and it's a story of it's not an engineer, but it's a technician going around the world building bridges and towers and let's say in steel kind of elements like this. And I like it very much because you really feel the passion for a well-done job. So if you don't know what a Christmas present, for example, if you find it somewhere in a bookshop, have a look to it, because, well, it's a little bit local in the sense that sometimes this author uses some phrases that are common in my city, so that's why maybe I like it more. But it's really when someone likes to do his or her job and tries to do the details. So when you said quality of the measurements, it means do a well-done job, not just stop there and say, okay, I take some measurements. No, it's not some measurements. It's the measurement we need. Otherwise, it's useless. And we study a lot to be able to distinguish between what we need to what is just noise. That's why I suggested the book. That's it. En español también.
Thanks. In the case of the pendle sensors, the variation of the frequency, the angle, say something about the type of avalanche?
No, no, it doesn't. You know, you would, in this particular application is just open and close, 0 and 1.
Ah, okay.
So when you go beyond a certain angle, it means we have triggered it, so something is happening. In order to go for what you are saying, you would need to mix many other information, meteo station information, for example. You would need to have more detection sections to see the velocity of the avalanche, because you see a detection here, detection there. You know the time when this occurred, and you can compute the velocity, for example. So to know more about the phenomena, you need more data. This is just open and close, as it is.
Okay. There is a question on the YouTube channel. It says, how to detect false movements registered by the sensors due, for example, to air movement?
Yeah, that's a very good point. If maybe I go back, I could also connect. Yeah, if you see here, and earlier I mentioned that the meteo station is a very important tool together with the others, because we can measure precipitation, snow and rain, and also wind. And other factors. So for example, yes, it is true, if we have very strong wind, and in the mountains, in the channels, we might have very strong wind, this will wave and move. The weight is not that small to avoid it, so that you don't move that much, but they might move. So they could trigger the alarm. So how to understand if it's a false alarm or not? Well, here we will also see, we should go down in the figure, we don't see it here, but we would also see the wind speed in that particular moment, so we can judge ourselves if it is a false alarm or not. And for example, we could also build algorithms so that we change the threshold on the basis of the wind speed. If the wind speed is higher, we take a higher threshold, for example. So there is some engineering that we have to do there to avoid this kind of false alarm. But meteo station, meteo data are important in that perspective.
Perhaps I have some question. I saw in one of the slides the word time scale coefficient. What is the
I'll tell you
what
why.
does that mean?
Yeah, I tell you why it's there. Because I was saying here that we build scenario analysis by using our numerical models. Then if we are lucky that we have back analysis, and in this particular example that we studied in the last years, we had a small instability that we could back analyze with the same model. And when I say back analyze, it means that we get a validation of the geotechnical parameters that we're using in our numerical model, but also of the evolution of the landslide. So if we are able, for example, with a distinct element method to study not only the triggering, but also the evolution, from the back analysis, we can validate the evolution. What do I mean with that? I mean, where do the collapsed material stop? At what distance? How much time, and that's the time scaling coefficient, how much time do they need to go from the original position to the position at rest? So if we know that in reality, we can somehow make the model to match them. And in this particular example, we had to scale the time of the modeling in order to make it match the real occurrence of the phenomena. So that's why we call it a time scaling coefficient. We scaled it from modeling to the real site. That's why I think that having monitoring data and the possibility to run back analysis is very useful for this purpose, because you can really be confident on the modeling you're doing.
Okay. I don't know if there is another. Yes.
Another question for the YouTube channel: how climate change is affecting the monitoring system for phenomena that may affect civil infrastructure?
How do climate change signals affect? We would need to look at specific predictions on the different areas of the world. In the area I was mentioning, which is the northwestern Italian Alps, we see a change in the occurrence of the intense precipitation. And since debris flow and snow avalanche are directly related to intense precipitations, this is how climate change signals are affecting these phenomena in this kind of way, by changing the occurrence of the phenomena. Maybe we were used to have debris flows in May. Now we maybe have it in a different month, or for example, or we were used to have them once every 10 years. Now we have it once every 5 years. Okay, this kind of aspects.
And the last one: how ash flows in active volcanoes can be monitored and their trajectory?
Wow. I should say I don't know, because it's really out of my... There is a lot of snow in the mountains, so we don't have... and we don't have any volcanoes in the area there. But So how should you do that? Well, I would say without, we need to use sensors that are remote kind of sensors, like the radar, for example. Like you can also use ultrasonic sensors, the ones that they are used also in water engineering to detect the water table, not the water table, the height of a river, for example, when you have a flood. You can measure that. So those are probably the kind of sensors that one could use. But in order to do detections like this, you will need to have a nice prediction of the direction of the phenomena. I don't know if this is really that easy to do. I don't know. I'm really not an expert in this. What about you? What do you think?
Thank you very much for the presentation, Dr. Barla.
Thank you.
So we have a small
thank you.
announcement and a present for you. So thank you very much for accepting this invitation and for delivering this nice presentation.
Thank you.
I think we need to take a picture.
A photo. Okay.
Yes.
Great.
Can we go?
Of course.
So maybe one with the presenter and then I go.
1, 2.
Thank you very much. Oh, thank you. It was a very nice presentation. So again, thank you very much to Dr. Barla to accept giving this very interesting presentation. We have another talk. Tenemos otra charla. Ya pasamos a español, lo siento. También tenemos la charla del maestro en ingeniería Edgar Montiel, que iba a estar aquí presente, pero porque viene para el Congreso de Amitos, pero desafortunadamente por cuestiones personales tuvo que mover su vuelo y ya no pudo acompañarnos para esta charla aquí en el Instituto de Ingeniería. Sin embargo, nos hizo el favor de preparar un video de la presentación que vamos a proyectar en este momento. Entonces, antes de proyectar el video, me gustaría leer rápidamente una semblanza del maestro en ingeniería Edgar Montiel. Un segundo. El maestro en ingeniería Edgar Montiel es ingeniero senior y jefe del grupo de modelización numérica de SRK Consulting Group en Chile. Cuenta con 15 años de experiencia en geotecnia aplicada, ingeniería civil y minería. Lidera estudios de modelización numérica en medios continuos y discontinuos, desarrollando estudios para proyectos mineros en Chile, Sudáfrica, Estados Unidos, Australia, Perú y México. Recibió la medalla Alfonso Caso por el mérito académico de la UNAM. Es autor de 29 artículos técnicos en congresos nacionales e internacionales y revisor de la Slope Stability in Mining Conference de Australia desde el 2021. Cuenta con más de 5 años de experiencia como docente en la UNAM y es director de tesis de posgrado en geotecnia y modelización numérica. Entonces, de nuevo, agradecemos mucho al maestro Edgar por preparar la presentación, a pesar de que tuvo que posponer el viaje. Y por ahí le pedí, en las diapositivas, por ahí debe de aparecer el correo electrónico. Si tienen alguna pregunta, pues les agradeceremos que le escriban un correo directamente para externársela, pues al no estar aquí no las podrá responder.
Hola, ¿qué tal a todos? Muchas gracias por su asistencia a esta presentación. Mi nombre es Edgar Montiel, soy maestro en ingeniería por parte de la UNAM y actualmente me desempeño como jefe de grupo en SRK Consulting Group en Chile. El área en donde funjo es el área de modelado numérico y estamos encargados de hacer simulaciones y análisis tanto de minería a cielo abierto como de minería subterránea. El tema del que les voy a platicar ahora es un tema relacionado directamente con mecánica de rocas y con modelado numérico. Particularmente, vamos a tratar una metodología que he venido implementando con el grupo ya desde hace algún tiempo y que fuimos capaces de publicar el año pasado. Esta metodología tiene la particularidad de que adapta varios conceptos de las redes de fracturas discretas, es decir, de una metodología, una lógica de naturaleza estocástica para representar estructuras, lo adapta de forma determinista para poder incorporar dentro de los modelos que se generan, los numéricos, los sistemas y las estructuras que están definidas por geología, por la geología estructural, que pueden afectar la estabilidad de nuestros taludes, y incorpora cada una de estas estructuras de manera determinista, es decir, las ubica espacialmente de acuerdo a que fueron tomadas con sus características estructurales, es decir, persistencia, desplazamiento, etc., de acuerdo a cómo fueron tomadas en la realidad. Vamos a ver que esta metodología tiene algunas revisiones capaces de ajustar la persistencia como parámetro complejo, dada la limitante que tiene la lógica de las redes de fracturas, y hace un estudio también dirigido a la evaluación de la dimensión. Luego de empezar esta ponencia, vamos a hablar un poquito de los objetivos y la motivación de esta presentación. Principalmente es presentar una metodología que permite la incorporación de discontinuidades con persistencia definida, este concepto va a ser fundamental, cuando se utiliza el método de elementos distintos, ¿vale? Esta metodología y este uso del método está muy dirigido al análisis de macizos rocosos, ¿vale? Los ejemplos que vamos a tratar acá pues, son dirigidos esquematizados completamente dentro del ambiente de los taludes, de la minería Cielo Abierto, y profundizando, esta metodología presenta dos particularidades principales. La primera de ellas es de índole práctica, es decir, a través del uso de los compiladores y de las suertes de programación, en donde se adopta la lógica estocástica de las redes de fracturas discretas, de las DFMs, vamos a ver qué es eso con detalle, y se utiliza esta para resolver particularmente la disposición espacial de las estructuras, pero de forma determinista. La segunda es más bien algo de índole teórico-técnica, va a atacar conceptos fundamentales dentro de la caracterización y la aplicación de la estabilidad, en donde se va a evaluar el impacto que tiene la rugosidad de las discontinuidades. Vamos a ver que no todas las estructuras que podemos mapear, y sobre todo para las dimensiones que tenemos los rasgos de Cielo Abierto, las estructuras no siempre se presentan como elementos completamente planos. En muchas de las ocasiones presentan cierto nivel de sinuosidad. Entonces nos enfrascamos en verificar cómo impactan estos niveles de sinuosos, rugosos, dentro del concepto de estabilidad global. ¿Vale? La motivación principal, como ya dijo hace un momento, recae en poder mostrar un poquito la metodología que fue presentada y publicada en 2022 en la tercera conferencia de redes de fracturas discretas celebrada por la Asociación Americana de Mecánica de Rocas, y que tuvimos la oportunidad de presentarlo en la Universidad de México. Entrando un poquito en materia y dando un poquito de contexto, vamos a ver un tanto qué son las redes de fracturas discretas, sobre todo para familiarizarnos en el mismo lenguaje. Las redes de fracturas discretas prácticamente son la representación en un modelo de las distribuciones de estructuras que existen en la naturaleza. Normalmente nosotros nos encontramos con los macizos rocosos en esta forma, y una vez que los tratamos de estudiar, tenemos que encontrar sus arreglos estructurales. Los vamos representando, los vamos viendo, los dibujamos, los medimos el espacio, la distancia entre estructuras, la persistencia, cuánto miden de longitud, qué arreglo estructural hay, es decir, qué estructuras fueron primero, cuáles después, de acuerdo con sus familias, y vamos agrupando toda esta información normalmente en redes estereográficas, en bases de datos, en toda una connotación geológica. Vamos a ver que no siempre estos datos son puntuales y simples. Pensemos en la escala en la que trabajamos a nivel humano respecto a estos taludes y a esta condición pues, enorme cuando vamos a estos taludes de que son entre 15 y 20 metros, cuyas agrupaciones de taludes uno tras otro llegan a darnos alturas de PIB o de mina a cielo abierto que llegan 200, 300, 500 metros de altura. Entonces vamos a darnos cuenta que estas redes estructurales no siempre se nos presentan de una manera organizada, con el mismo espaciamiento y la misma distancia entre fracturitas. Tienen arreglos que podemos llevar a la comprensión a partir de distribuciones probabilistas, ¿vale? Una vez que obtenemos esa información, una de las vías en las que las vamos a representar va a ser a través de estas redes de fracturas discretas. Acá abajo tenemos unas visualizaciones, por ejemplo, de redes de fracturas en 2D, trazas prácticamente de líneas, las cuales cortan entre sí y se unen, van dando forma a las estructuras y a sus arreglos de contacto. A la derecha vamos a ver un arreglo tridimensional, como lo veríamos en la forma 3D. Cuando lo hablamos en 3D ya tenemos que pensar no solamente en líneas, sino en superficies. En este caso las superficies normalmente se representan a partir de discos. Una vez que tenemos estas distribuciones y que podemos dibujar de forma probabilista todos estos arreglos de discos y ya encontramos las disposiciones tanto en su ubicación espacial como persistencia, en este caso la longitud que tendría la línea en 2D o el diámetro del disco en 3D o el espaciamiento que sería la separación que tiene se va a colocar de forma va a estar colocada en función de la distribución que hayamos definido, el espaciamiento, o sea la distancia que hay entre estructuras, que lo tenemos ya definido y completamente concretado. Vamos a poder armar modelos que pueden ser incorporados a los análisis, en este caso geotécnicos, a los modelos de esfuerzo de formación, a los modelos de cálculo que normalmente utilizamos en la práctica para este tipo de evaluaciones. Aquí, por ejemplo, les presento un modelo de DFNs publicado por Rogers, un grupo también de minería, en el cual aplican una red de fracturas a una excavación subterránea, a una oquedad, y van evaluando de forma estocástica distintos arreglos y distintas distribuciones que les van a permitir evaluar el tamaño máximo de bloque que va a existir dentro de esa oquedad y para el cual tendrían que estar preparados en el caso de que quieran entrar a intervenir o colocar algún tipo de soporte en el techo. Esta función acumulativa va hablando de esa acumulación de altura, todas las iteraciones que generen, y permitiéndoles ver desde el punto de vista estocástico cuál es el volumen más representativo y aceptable dentro de estos criterios probabilistas. En el otro caso, van a ver un análisis que tuve oportunidad de hacer en 2020, una publicación con los australianos, en donde se evalúa prácticamente lo mismo, pero ahora aplicado a un rajo a cielo abierto. Hacer un análisis estocástico en donde se estudiaron todos los arreglos estructurales de una mina y en función de las distintas regionalizaciones que tenía en el sector se definieron distintos niveles de diaclasas, persistencias, fracturamientos, etc. Y se hicieron muchísimas pruebas, ¿no? Alrededor o sea, muchas pruebas, y de ahí se volvió a obtener ahora una curva, pero de volúmenes, los cuales nos permitieron ajustar el valor que estaban obteniendo en la realidad para identificar ya con ese carácter de volumen que tanto estaba influenciando en la red de fracturas discretas y en consecuencia poderlo aplicar a modelos predictivos en donde, sin avanzar la excavación, se iba a lograr un talud más alto y ver cómo iba a impactar estas disposiciones estructurales. es lógico que se pregunten, bueno, pero prácticamente estás diciendo que estructuras que podemos tener posicionadas en la realidad, ¿les vas a dar carácter aleatorio? Sí, porque pensemos que en muchas ocasiones lo que vemos en la superficie no sabemos si va a continuar igual a 200, 300 metros de excavación en profundidad. En el caso del Open Pit, ¿no? El caso del estudio de la izquierda, aquí en la diapositiva, es un estudio único, no necesita carácter predictivo. Entonces, es ahí el fundamento de esta naturaleza, ¿no? Cuando ocurre eso, y profundizando, cuando ocurre esa duda personal, es donde vienen los cuestionamientos que le dan origen a la metodología que voy a presentar ahora, ¿no? Cuando vemos estas dispersiones y el hecho de decir, bueno, ¿es cierto o no? Pero ¿qué pasa si ya tengo las estructuras definidas y el geólogo alcanzó a mapear todas las estructuras de la mina? ¿Cómo lo calculo? Quiero conservar su posición exacta, ¿no? Entonces, ahorita lo vamos a ver cómo se resuelve. Para resumir, el carácter que tiene esta metodología es utilizar esto que están viendo en pantalla, los disquitos, las distribuciones, la estadística, los estudios de geología, la resolución de datos, para poderse aplicar, pero ahora de una manera exacta, a un rajo, en este caso, con las estructuras mapeadas por los estudios geológicos. ¿Cómo conseguimos eso? Vale, es común en el ambiente de estos rajos a cielo abierto que nosotros recibamos una cantidad enorme de estructuras cuando tenemos que simular una pared o todo el open pit completo. ¿Cómo hacemos para poder dibujar estas estructuras? De ahí es donde viene la base de esta metodología. Esta metodología va a utilizar el fundamento que tiene el análisis estocástico que les mostré anteriormente para poder generar los discos de manera puntual, o vamos a llamarle determinista. ¿Cómo? Bien, dentro de la lógica que utilizan los softwares, en este caso de elementos discretos, para representar redes de criaturas discretas, sucede que tú puedes incorporar tus funciones de distribución desde fuera, obteniéndolos en datos por hojas de Excel quizás, o en hojas de evaluaciones personales, y tú puedes suministrar la posición XYZ de cada estructura, el diámetro del disco, la orientación, el deep direction, o sea, para dónde busa, para qué inclinación tiene, y lo dibuja, ¿vale? Pero recordemos, son discos, en el caso tridimensional, son discos, ¿vale? Entonces, nosotros lo que recibiríamos, pues no es esa información, lo que recibimos son mallas, triangulaciones de cada una de las estructuras con sus características. Bueno, en este caso, la metodología lo que hace es que toma esta estructura, una triangulación, la circunscribe en un círculo, ¿no? Y a ese círculo le saca los datos que queremos para poderlos representar en el espacio, ¿vale? ¿Qué deficiencias tiene a primera vista? Bueno, aquí los pueden ver, este es un modelito donde tenemos las estructuras físicas mapeadas en la realidad y los discos que generan. Normalmente están sobredimensionados, ¿no? Acá arriba se extraje uno para que lo puedan ver. La estructura, en este caso el plano estructural, tiene una traza definida, son de cientos de metros, y el disco que genera es gigantesco, ¿vale? Al generar este disco tan grande, tan enorme, lo más seguro es que si nosotros quisiéramos evaluar la estabilidad de esta pared, en esta sección que les estoy señalando, bueno, van a ver que hay una daylighting, una cuña falla no florante, una estructura no florante, en toda la pared, cosa que no es real, puesto que el plano estructural ligeramente corta en alto de 2 o 3 bancos, ¿vale? 2 o 3 taludes en la parte más alta del talud. Entonces, hasta este momento, la representación que habíamos conseguido, pues no era tan fiel, ¿no? Daba cosas muy sobreestimadas y sobre todo del lado de la inseguridad, ¿no? Sin respetar las características geológicas de las que estuvimos platicando. Haciendo una suerte con los softwares, en este caso de programación que tienen el mismo programa, y definiendo un box limitativo, es posible que este disco rojo lo podamos afectar a un disco truncado, a un disco cortado, ¿no? Y generar en ese caso una estructura muy parecida al plano que nos suministran con las triangulaciones. Inmediatamente, para los que me entiendo, existe un problema. Las estructuras, y aquí ya lo pueden ver desde aquí, desde esta imagen, las estructuras tienen cierta ondulación, ¿vale? ¿Qué hacemos con esta ondulación? ¿Cómo sabemos que nuestro plano va a representar lo que queremos, va a calcular lo que queremos si tiene esa cierta ondulación? ¿Vale? Hasta este punto nosotros ya habíamos conseguido una metodología que nos permitía incorporar desde centenares de estructuras, no sé, 300, 500 estructuras, pero tenemos esta limitante de la rugosidad. ¿Qué hicimos? ¿Qué hicimos al respecto? Bueno, lo primero que se evaluó, que se midió, pues fue revisar qué había al respecto del estudio de las estructuras onduladas, cómo se representan y qué impacto tienen, ¿vale? Acá en la figura ustedes pueden ver, por ejemplo, a lo que me estoy refiriendo, no todas las estructuras son planos perfectamente lisos, tienen saltos entre los bancos, que bien se podrían modelar en caso de ser pocas estructuras. Ojo, vean este modelo que es más pequeño, tiene 4 estructuras, las cuales pues respetan completamente la sinuosidad del elemento, ¿vale? En lo que estábamos hablando anteriormente son cientos de estructuras. Entonces, ¿qué fue lo que hicimos? Haciendo la evaluación técnica de la información que encontramos, bueno, vimos que existen algunas publicaciones que ya están la naturaleza de estas ondulaciones, ¿vale? Las clasifican, permiten su clasificación. Entonces tomamos están referidos en el paper, quien quiera revisar, y aquí también escrito. Entonces, las tomamos y planteamos lo siguiente, dijimos, bueno, esta rugosidad va a actuar en el talud. ¿Cómo la podríamos evaluar? Bueno, pues dibújala en un modelo local, sencillo, dibuja una estructura con su rugosidad y después a esa rugosidad sácale su disco y dibuja otro modelo donde tengas el disco representado, ¿vale? Compáralos. ¿Qué diferencias hay? Haciendo ese ejercicio, pueden ver acá a la izquierda, un modelito con la estructura perfectamente dimensionada bajo los estándares geométricos que están normalizados en las publicaciones, en este caso de la Sociedad Internacional de Mecánica de Rocas, incorporado completamente bajo este esquema rugoso, y otro modelo en donde el disco queda inmerso como resultado de la metodología que estamos aplicando. Evaluamos cuál era el efecto, en este caso del puente de roca, que podría ocurrir en una estructura no aflorante, para ver qué puede pasar, cómo varía la resistencia, qué efectos hay. ¿Qué conseguimos a partir de esta serie de modelos y de cálculos que hicimos con distintos perfiles de rugosidad? Considerando un modelo simple, cuya resistencia estructural fuera muy baja, por ahí tiene un dato, 11 grados de fricción, estructuras muy completamente cisalladas, y dándole parámetros de macizo rocoso de ejercicio únicamente, nos dimos cuenta de algo. Los resultados eran diferentes, daban cosas distintas. Poniéndonos un target tipo back análisis, tratamos de llevar la condición de la resistencia, en este caso el GSI, para los que estén familiarizados con los macizos rocosos, el GSI o el índice de resistencia geológica, Geological Strength Index de Hooke, te permite evaluar o integrar la calidad de roca en cuanto al efecto escala que puedes tener en tus mediciones de campo respecto a la realidad y el efecto que va a tener que el modelo constitutivo de fluctuogramos. Entonces, ¿qué fue lo que hicimos? Bueno, buscar el valor GSI que nos permitiera llegar por back análisis a un factor de seguridad de 1 en cada caso. Y obtuvimos algo bastante interesante. Para todas las estructuras que fueron modeladas de forma rugosa, explícita, vamos a llamarle GSI con un subíndice R, rugoso. Y para su contraparte simulada con la claricidad, vamos a llamarle GCI L, ¿no? En este caso representa la lineal o smooth, el más planito. Y vamos a ver la comparativa que hay entre los GCIs que necesitamos para llegar al valor de gráfico análisis. Comparando, vemos que conforme estamos en el ámbito, vamos a decirlo, planar, poco ondulado, la comparativa se presenta bien, hasta un 96% de precisión, requiriendo cambios mínimos en el criterio de GCI, o sea, un valor de risa. No así cuando empezamos a tener rugosidades de importancia, ¿vale? Ondulaciones rugosas de trascendencia, ¿vale? Cuando esto ocurre, vamos a ir viendo que la relación que existe entre un valor y el otro tiende a ser alta, siempre mayor para los planos lisos, lo cual ¿qué nos dice? Bueno, en resumen, nos dice, oye, de forma unilateral no metas todas tus estructuras y las modeles con esta metodología, revísalas, dales una mirada previa, y si es necesario, si no funcionan, mételas como en la diapositiva anterior, mételas onduladas, las que sean, ¿no? Si no, no vas a obtener resultados realistas. Vas a tener un sector demasiado inestable, que en realidad tendría que ser más estable por el efecto de la revolución. Una vez conseguida esa validación, y evidentemente después de haberla revisado con suficiencia de datos, es decir, muchos ejercicios, nos dispusimos a aplicarla en un proyecto, ¿vale? En este caso, antes de empezarlo a hacer de forma continua, primero revisamos qué ocurría con un sector que ya había fallado. En el proyecto en el que estaba trabajando, ocurrió que, bueno, teníamos que partir con la información del terreno, 140 estructuras levantadas, pero había un sector que había tenido un fallamiento de 2 bancos. Entonces, bueno, si la metodología funciona, tenemos que hacer la detección y ese sector tendría que fallar, ¿vale? ¿Qué ocurrió? La calibración requirió sí evaluar la resistencia de la roca. Es bien común que los parámetros de laboratorio y de caracterización, sobre todo del macizo rocoso, tienden a ser muy buenos respecto a lo que se ve en la realidad. Pero en realidad la calibración requerida aquí fue muy poca, es decir, fue un castigo de propiedades muy limitante en el caso de algunas variables que no se habían considerado, que estaban exprofesas en medio, como la cantidad de la diferenciación de resistencia que había entre una capa y la otra, para que se consiguiera el factor de seguridad, en este caso cercano a 1 del sector, y con eso validar la calibración. ¿Qué más nos ayuda? Bueno, la similitud que tiene el mecanismo de falla respecto al mecanismo real. En este caso, la intervención de las estructuras claves para el desarrollo de la inestabilidad, dándole así un check a nuestra calibración. El segundo caso, ya para terminar, el segundo caso que les presento fue un análisis predictivo en otra mina, en donde, acá a la izquierda van a ver, bueno, aquí tiene el resultado del mismo modelo, pero con 3 variaciones. ¿Qué ocurría? Que, bueno, de la mitad, vamos a poner aquí donde está el láser, se tenía un avance en excavación, es decir, se excavaba todos estos bancos y se liberaba un bloque no aflorante de muchos bancos de altura. Consideren que cada banquito de estos tiene alrededor de 15 metros de área. Entonces, la predicción original, que tenía las estructuras como las había mapeado originalmente en geología, consideraba todo este lado, que está representando esta fotito aquí en este acercamiento, todas estas estructuras con muy gran persistencia, ¿vale? Posteriormente nos dijeron, oye, vamos a levantar todo un modelo estructural, porque no creemos que esas estructuras sean así. Fíjate que tenemos evidencias de que no son tan largas. Entonces, un punto bueno de esta metodología fue que no fue necesario esperar la interpretación completa de geología, solo les pedimos los datos, qué estructuras y qué distancia tenían, y el primer intento fue, oye, no todas las estructuras son de alta persistencia, de alta continuidad, ¿no? Solamente algunas, aquí pueden ver, las quitamos, inmediatamente vimos que el factor de seguridad cambiaba, respondía de manera lógica, pues estás quitando estructura, estás quitando elementos de borde al mecanismo de falla. Y después nos dijeron, ¿sabes qué? No, acabamos de ir a terreno, de hecho fuimos a terreno, revisamos las estructuras, no las vimos, y hicimos el último modelo, en este caso acotando más aún esta familia de tren estructural que pensábamos que existía en el sitio, dejando un mecanismo de falla mucho más pequeño, más acotado y más acorde a los volúmenes de roca que se podrían esperar en ese tema. Entonces, de carácter predictivo, nos ahorró bastante en cuestiones de tiempo, nos permitió hacer esta prognosis de conocimiento del comportamiento y sobre todo nos ayuda a establecer una relevancia, en este caso trascendente, de la persistencia, que, como vimos al inicio, es uno de los inputs de nuestra información geológica. Listo. Dicho eso, bueno, conclusiones, ¿vale? Este artículo pues presenta una metodología, en este caso de modelización, que permite la incorporación de muchas estructuras a los modelos numéricos de macizos rocosos. Aprovecha las capacidades de las lógicas de la DFN, de las redes de fracturas discretas, para permitir cambiar un tanto el enfoque estocástico por uno determinista y hace los ajustes de imprecisión que tiene el uso de los discos de manera natural. En este caso, acota los discos a una persistencia real. Adicionalmente, la metodología presentada demuestra, a través de un ejercicio de comparación en los movimientos lisos y rugosos, pues que hay que tomar en cuenta la rugosidad, ¿vale? Desde una perspectiva un tanto cualitativa, desde la primera visión hasta un punto cuantitativo, nos indica qué rasgos son los que tenemos que buscar a la hora de generar estos modelos, permitiendo así la interacción con la gente de los geólogos y asumiendo un rol más decisivo para los modelos en cuanto a la capacidad de revisiones que pueden generar, no acotándolos únicamente a una decisión de datos, de esto me dio el modelo, sino no, ahora ya te permite que modifiques con un T-clase la persistencia de estructuras y que puedas llegar a una conciliación realista de lo que están viendo en la realidad. Esta evaluación concluye que en el caso de las discontinuidades que sean muy rugosas, o muy rugosas, deben de ser modeladas de forma explícita, ¿vale? Completamente dibujadas con sus trazas, para que se puedan incorporar las ondulaciones y obtener los factores de seguridad que son. Finalmente, la metodología se muestra como una ventaja práctica, respaldando el estudio de los taludes, en este caso del Open Pit, y revela cómo el modelo estructural termina siendo un factor clave, el cual debe ser robusto, debe ser lo suficientemente claro para el geotécnico, el cual pues permita que a través de la comprensión de la caracterización, la categorización estructural, pues podamos representar de una forma precisa el comportamiento del terreno. ¿Vale? Espero que esta presentación les haya gustado. Por favor, siéntanse libres de mandarme un correo, ahorita les voy a dejar mirar. En esta diapositiva les pongo un poco las referencias, estas las pueden encontrar en el paper, a quien esté interesado. Y bueno, aquí están mis datos, les dejo mis correos para quien tenga alguna duda o algún comentario, por favor, consiéntanse con toda confianza de hacérmelos llegar. De antemano, muchísimas gracias por su atención y le quiero extender un agradecimiento particular al doctor Mánica por su apoyo para llevar a cabo esta presentación. Un saludo a todos y espero que en alguna ocasión podamos vernos. Hasta luego.
Bueno, pues muy interesante charla respecto a la caracterización de las estructuras geológicas en proyectos de minería. De nuevo le agradecemos a Edgar y le recordamos que por ahí apareció su correo electrónico, le pueden hacer llegar directamente cualquier duda que tengan a él. Entonces, fuera de eso, quizá nada más invitarlos más tarde a las 4 habrá una charla, no sé si tenemos por ahí el flyer. que organiza el Comité de Flujo de Agua a las 4 de la tarde. Estará un profesor muy reconocido de Texas A&M, Marcelo Sánchez. Entonces, si tienen oportunidad, Geotecnia para la Energía, desafíos y oportunidades, si tienen oportunidad de conectarse más tarde después del almuerzo, también es un tema muy, muy interesante. Fuera de eso, pues simplemente agradecer la presencia a los que están aquí en el auditorio, muchas gracias, y así como a los que se conectaron de manera remota. Les agradecemos mucho su atención y les reiteramos que si tienen alguna pregunta de la charla anterior, pues se pueden poner en contacto directamente con Edgar. Pues muchísimas gracias a todos y buena tarde, buen provecho.